Good afternoon.
Hello.
Why am I on here twice? Okay. I have this second, I'm trying to resolve this second occurrence really quick. Great. All right. I think I figured it out. Let me pull up our slides. Okay, let me just grab attendance really quick. I'm going to switch screens here. Okay. All right, looks like we have a full class. That's great. I hope everyone's having a nice week. Okay, so last week we covered probability at a fairly introductory level, not pleasant, or this still says probability. Sorry about that. So I recognize that there was probably more math involved last week than you all wanted to deal with, but unfortunately, there's really just no getting around some basic math. We stayed away from deriving equations or digging into the math too much and tried to keep it pretty high level and let Excel do most of the work for us. So we're going to kind of keep that theme going through this week and next week. There's less, this week is a lot more about methodology and sampling. There's a couple of things that we're going to calculate, but we're going to use Excel again to do all of our heavy lifting. And then for next week, we'll go into hypothesis testing, which is kind of like a different methodology for doing what we're doing this week. So that kind of buckets introductory sort of basic core concepts for data analytics type of work. And then from there, when we go on to looking at specific types of methodologies like regression, you'll have the background that you need to understand and interpret and analyze the results of those types of analytics. So we're going to talk about methods, take a break, cover the estimation side of things, hopefully take another break, and then have our discussion about prescriptive analytics. I do have to be done today. I do have a hard stop at around 3:20, so we won't be going over today for sure. If there's a lot of questions or we don't get to going over this week's assignment, then I will set aside some time. I'm already planning to set aside some time on Saturday to walk through and help one student, so we can kind of open that up and or the end of that up, and you guys can jump in if you'd like and ask questions, or if you're stuck, you can chat with me then, because I want to make sure everybody's getting their homework in. I don't mind if it's late. If you've reached out to me and are, working on it actively, I won't penalize you for that. I know we all have busy lives and things going on, and some of this content might be a little more difficult than what you're used to. So I want to make sure everybody succeeds in this course. All right, so we talked about probabilities. Now we're going to talk about sampling. When we're trying to get information about one or more characteristics in a population, we generally can't capture data from every single member of that population. And we touched on this a little bit in last week, but this is kind of the focus of this week. So we need ways to identify a representative sample of the population that we want to measure information about, and then get the information from that sample size. And we're going to cover the sampling schemes, which is the first part of our discussion. And then we're going to show how we can take information about a sample of a population and use it to infer information about the entire population. So that's why you see the term inferential statistics. That's all that means. We're using information about a portion of the population to infer information about the entire population. And there are some rules that have to be in place in order for that to work. So when we say population, we're saying the set of all members about which a study intends to make inferences. So one question that people got wrong a lot when we talked about a population versus a sample last week was we were talking about an analyst wants to know if 9/11 changed people's anxiety about flying. And so they want to do a survey. So what is the population there and what is the sample? So the sample part was easy. That was the 1,500 people that they sampled. The population, a lot of people said, was all US citizens. But in actuality, we really only care about all US citizens who fly commercially. So we went a little too broad with our responses in that it has to be the relevant population. So when you're trying to think about what the population is, keep in mind, like if you're doing a survey about home ownership in the US, the population isn't all US citizens, it's all US citizens who are homeowners. So just to be extra clear about what that means. A frame is a term that like data scientists use a lot. It's just a list of all the members in the population. And if you get into like the Intro to Python course, you'll see the term data frame a lot, and it's just the key data listed out in a nice table. So it's just all your population members. And the sample members within that are your sampling units. A probability sample is a sample where you choose the units based on some random mechanism that's usually calculated via like a computer. And a judgmental sample is when like I would personally go in and like hand select samples. We're not going to do any judgmental sampling, and in general we would avoid that because it's very hard to justify an audit and ensure that it's random. I would think like, yeah, okay, we're just going to move on because we're not going to deal with that. So when we select random samples, there's a couple different things we can do. So the key takeaways here are that the more accurate or the more complex or precise your sampling scheme is, the more expensive generally. So there's usually a trade-off between what's simple and affordable or simple and easy versus what's more robust but takes more labor, is more expensive. All right, so simple random sampling, we have, we're choosing n number of options from our population. And these are pretty straightforward. I'm gonna show you a picture of what this looks like because I think it's easier to for some people to visualize. So simple random sampling, we, like it says here, in real life, generally we would choose a more complex method, but understanding simple random sampling is important for understanding all the different branches of, or methods that branch off from it. So let's say our population, which is capital N, is 5, and we're selecting random sample sizes of 2. There's 10 total samples that we could get from this. And they give you a methodology for doing this in Excel, and we'll look at it, but you could use the random function, and you could take your 10 samples and just say, okay, everything from 0 to 0.1 is sample 1. Everything from 0.1 to 0.2 is sample 2, and then let the random function randomly decide which sample corresponds. But just to be clear, so if the population is 5, that's our A, B, C, D, E. And how many permutations of 2 can we pull from this? So we have AB, AC, AD, AE, BC, BD, BE, CD, CE. So there's your 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 potential samples. And so you would assign, say, like AB is from 0 to 0.1, and then AC is 0.1 to 0.2. So you would make those assignments, and then you would use the random function, and it would decide for you which of these to use. That's a very, very simplified example. Okay, so if this is our, this is one way that they talk about doing this in Excel. And what they did is they took this information. It's a bunch of data about family incomes. And they copy pasted this information over. So there's 40 members of units. So they copy pasted it over. And then let me just paste these values. And then they took the random function and they ran it. So the random function takes no arguments. It's just one simple function in Excel, and it will always spit out a number, a decimal between 0 and 1. So in this case, 0.383. So it just randomly decides this. If for some reason you wanted to draw like random numbers between 0 and 100, you would take your random function and just multiply it by 100. Now I'm getting numbers between, and notice every time I run a calculation, it automatically changes because the way the random function is, whenever you recalculate a spreadsheet, it recalculates. So that's going to be a problem for us here in a second, and I'm going to show you guys how to get around that for this exercise. But so I just wanted to point out, this is how you get like a random number between 0 and 100. There's other things you could do. If you needed it to be an integer, you could throw the integer function around this, and it would automatically round for you. So now it spit out 5. So if you need the random function to do something specific, you would have to kind of get clever about what you're doing. Same thing if you need to be between a number between 0 and 10, you'd multiply by 10, and so on. So I need these values to stay put now that I have my random values in here, because what I'm going to do to get my sample of 10 is just select the bottom 10. That's the decision I made going into this. So if I copy this data and I right click, there's an option here to paste values. I'm going to do that because I need this to be fixed. And then I don't want it to recalculate anymore, because then everything's going to change every single time I open this spreadsheet, and it won't be in order anymore. So now I'm going to select all 3 columns and come up here to sort and filter. I'm going to go to custom sort, and I want to sort column F. I want to sort it from smallest to largest. And so you can see it did that. And I should have taken the highlighting off because it was from before. So my top 10 samples are right here. 1, 2, 3, let's see, 9, 10. And you can see it just randomly pulled. So it just so happens that like the 2nd, 4th, the 29th number in this sample of 40, these were the 10 random results. And that's one way to pull a sample. They also gave us a little spreadsheet where they randomized it by building out some macros. Don't worry about this part of the example, just letting you know it's here. For those of you who are more advanced with Excel, if you have played with macros at all, you could dig into this spreadsheet and look at it. But for anyone else, don't stress about that. Just letting you know it's there. Okay. So random samples. In real life, we don't use these very often. A lot of times, if you're applying this to a large geographical region, and you pulled a simple random sample, and you're trying to do something like personal interviews, you might get people all over the place, and so you'd be technically, and this is a very simplified example, but if you had to show up to those interviews in person for this thing you were doing, let's say it was like a psychology study or something, that would be very expensive. You'd have to travel to all those locations. So we wouldn't use it for stuff like that. It also means you have to know your whole population before you sample it, and that's not usually possible in larger applications. And then it can be a little bit biased in terms of how it represents part of the population. So it's not always a great approximation of the population. So there's one other way to get a random sample, and I am going to show this to you for those of you that did download the Stat Tools feature. Sorry, I got to get rid of this ribbon thing. Okay. So what I did, I was actually hoping I must have accidentally saved this file, but so I went into Stat Tools. I selected this data. It looks pretty plain when you open up the example file. It doesn't have the coloring and stuff. The reason it does that is I added it as a data set. So I went up to Stat Tools and I added it as a data set. It populated here. And then, so it has this variable for the account and then the bill amount. The bill amount is the one that I really care about. So now that I've added it as a data set, I can do this really cool thing with this tool here and create random samples. So let's say the example I showed you before, where we did the random and then we sorted and got the top 10. if you wanted to pull, like, say 25 random samples, you'd have to go do that rand sort, resort, pull the 10, like copy paste the values somewhere else. You'd have to do that 25 times. So the stat tools has a simpler way of doing that, where I can select the variable that I want to randomize, in this case, the bill amount, and I can tell it, I mean, I can tell it, give me 50, like run the simulation 50 times and give me 10 samples each time. And then when I run it, oh, sorry, I guess you can only go up to 25. It gives me a new spreadsheet with 25 random samples that it automatically calculated. So you could see how this would be an enormous savings time-wise. So now I have 25 random samples of 10. They took this stat tools data, they did this already, and they ran, they took the data and they put it into row format for all 25 samples and calculated the sample means. And then they generated a histogram. And the thing I wanted to show you about this, and remember the mean is just the average function. So you just have to put it in once, do your crosshairs, drag it down, and then you'd get the sample mean. Notice in this histogram, it kind of has a normal looking shape to it, a little bit. Just tuck that little note away for later, because we're going to talk about how, if we had been able to do this with 50, this shape would look more and more like a normal curve, like we talked about last week with probability. So that's going to be a key part of our discussion later. So I just wanted to point that out, the shape of this. And it's a good way also to check and make sure that they really are random. Okay, back to our slides. All right. Okay, so let's talk about some other sampling methods then. So another option we have is systematic sampling. In this sampling methodology, we divide the population size by the sample size to create blocks. So if we had a population size of 10 and our sample size was 2, we'd have 5 blocks of 2. That's not a great example. Let's say we have 100 and we're doing sample sizes of 10. We'd have 10 blocks of 10. Then we use a random mechanism to choose a number between 1 and 10, because that's our number for the block. And let's say that number comes out as 3. That's the first K member is selected randomly, and then every case member. So if we randomly selected 3 in our block of 10 members, it would be the 3rd member, the 13th member, the 23rd member, the 33rd, the 43rd, the 53rd, the 63rd, the 73rd, the 83rd, the 93rd. That would be our 10 in our sample. And that number K, in our case, in this example 3, is the sampling interval and represents the ratio of the population size over the desired sample size. So what does that really look like? In this case, we've selected every 3rd person, and they started with the 1st. So the 1st of 3, the 2nd of the next block of 3. Actually, here, let me. So in this sample, my tools go. Okay. We broke it up into blocks of 3. And then we selected the 1st member of each block. And that's how we got our random sample. All right, another sampling methodology is stratified sampling. So we could take subpopulations from within our total population, and we would call those strata. And then instead of taking like a random sample from the whole population, we would select random samples from each of those groups. And that's why it's called stratified sampling. So we would do this if we wanted to have separate estimates from within each stratum or class. And we wouldn't be able to do that if we randomly sampled from the whole population. So let's say we broke our population into like income groups, and we take random samples from each of those income groups. Now we can look at the entire population as a whole, but also we can look at the estimates that come from just the separate income groups. And there we might want to do that for that particular example. And then it also can increase the accuracy of the population estimate, because if we define those strata correctly, because it will reduce the variability within the individual strata than in the population as a whole. So if we're still talking about income, there might be a smaller group of very high earners compared to middle earners and low earners. And so if we break them out into those groups, we have a better representation of each group, and then also a better representation of the whole population, because we don't end up with a sample that pulls too many high earners from the total population. So like I said, the key to that is selecting the appropriate strata, and that's going to depend on what your objective is and what the product is. This would probably involve like a lot of meetings and maybe the marketing team, but the trick is that your sample sizes are proportional. So you want your stratum to be proportional to the total population. So for example, if the percentage of high earners in the total population size is smaller, then we would sample a smaller amount of those people in that strata. I think that's all I want to say about this, other than here's what that looks like. So we move our population into groups based on their similarities, and then we sample from those groups. The next method is cluster sampling. So they like the geographical reference of this, and I think that's fine in this case. So in this case, they separate the population into clusters. So they say like cities or city blocks, and then they randomly select clusters. And in real life, we would do this for convenience and then also for potentially lowering the cost, but it might reduce the accuracy when we're drawing inferences from the population, because we may concentrate on like clusters that are not as representative of the whole. So let's see. I think I'd rather just show you the picture. Okay, so this is similar to when we talked about systematic sampling, but instead of dividing our population up into intervals based on counts, we're dividing our population up into clusters based on, like in this case, cities, and then we're randomly selecting like a city. So in this case, like cluster 1 might be Seattle, 2 might be Portland, and 3 might be Boise. And then we're just gonna say, okay, randomly select a number between 1 and 3. It pulls up 2. So Portland ends up being the sample that we use. You can kind of see how, unless you pull a reasonable amount of clusters to sample, you might get a kind of a skewed representation of the population as a whole. So that scheme that we just talked about, where you might have like a list of cities and then you randomly select the cities as your clusters, that's a single stage sampling scheme. Polling agencies like Gallup, they use that scheme, but they use a multi-stage version of it. And all you really need to know about that is that they have a slightly more complex process for doing their nationwide surveys, where they have about 300 locations for the first stage of the sampling process. And then from that, they randomly select city blocks or other geographical areas for the second stage. And then they sample the households from those second stage areas. So they're kind of just adding like layers to get to their sampling group. And we're not gonna mess with that. That's like a whole, but the reason that we talk about it in this class is just to give you an idea of how complicated sampling can be. And the goal is always to be as close to the population as a whole. So we're trying to balance that complexity with accuracy. And for a company like Gallup, they need accuracy because that's their whole brand. If their polls weren't accurate, people wouldn't trust them, and then they'd stop citing them and they'd stop using them. So they have to invest in a methodology that's more complex so that they can be more accurate, because that's their business model. Okay, so we're doing really good on time, which is great, because I've kept you over the last couple of weeks. And also I think the second half of what we're going to talk about is probably a little more involved. So does anyone have any questions about the sampling methods themselves? Okay. I'm gonna, it's a little early to take a break, so I'm gonna keep going and we'll take a break at 2. Okay, so once we do this random sampling, we get into the whole point of doing that, which is estimating the properties of that sample in order to infer information about the population. So there's some mathematical procedures involved with doing that. And we're going to keep our examples to, simple random sampling, but these concepts scale up to even more complex sampling schemes. So the concepts are the same, just the math changes a little bit. So when we sample from a population, we introduce some error. And that's what we're going to focus on for the second portion of this lecture, is the sampling error. And it's an inevitable result of inferring information from a sample. So we talked about like Gallup and how they have this method, right? They care very much about their sampling error. They're trying to reduce it. So the more accurately they sample from the population, the less their error is. And we can calculate that error, and then we can kind of get an idea of how biased our sample might be. If we were to unequally select participants for a sample, we would call that selection bias. And I just want to introduce that term. It's not, the book doesn't really go in depth about it, but you might hear about that a lot. So if I'm doing a survey on US Americans, and my survey is conducted by people who own landlines, that's a selection bias because the people who own landlines are not the representative demographic they're representative of a specific type of demographic more than others in the US. For one, homeowners tend to own landlines far more than people who like rent. So there's that. And then also age. Generally, it's not the age group of people who own landlines is generally not representative of the age distribution of the US. Okay, there's also non-sampling error, and this is not due to randomness. This is due to usually bias. So especially with surveys. So a non-response bias is when a bunch of the sample just doesn't respond to a survey. And you could think of this as like CityU sends out course evals. And inevitably there's some non-response bias there because there's a large group of people that just don't respond. Non-truthful responses. So sometimes a question can be triggering for the respondent, or people get like fatigue filling out questions in questionnaires and they just start to answer whatever. With CityU, for example, maybe somebody gets really tired of getting the emails bugging them to take the survey, so they just go in and they just click all down, 5, whatever, they don't even read the questions, and then they send it forward. That would be a non-truthful response as well. Measurement error is when you have like a leading question or a very poorly worded question that's confusing, and so the question doesn't reflect what the respondent answered. And then voluntary bias is when the people who choose to respond, who volunteer their responses, don't really, they have some kind of bias. So in that case, like reviews for restaurants often have like a voluntary response bias because people who went and had an okay time generally aren't going to make an effort to go in and write a review or rank a restaurant. But people who either had like an outrageously amazing experience or an outrageously bad experience are far more likely to spend the time writing about it or ranking that restaurant than the people who it was fine. So that would be a voluntary response bias. Who's willing to respond to the survey and what drives them to want to respond? That can introduce some issues. So we can control these to a pretty good extent by sampling appropriately and by very carefully designing our surveys. And that could be a whole class in and of itself, but those things can be controlled. We can't control sampling error. That's other than by changing the size of our sampling, which we'll talk about actually, I think, next week. So some key terms for sampling. Point estimates are like the best guess we have of a population parameter based on the sample. So like the mean or the average of the sample is a point estimate. The sampling error is the difference between the point estimate of, say, that mean and the true value of the population parameter we're estimating. So if we have 40, actually in this example that we looked at, let's go back to here. Okay, so we have 40 items in our sample and we have 10, in our population, and we have 10 in our sample. So we can actually, in this case, we have the population and the sample, so we can calculate both the population parameters and the sample parameters. So you can see that the point estimate for the sample mean has some error, which is the difference between the population mean and the sample mean. So that it was off by 3,875. Every time we run this, that's going to change. See, in this case, it swung the other way. We could run it again. Now it's only off by 995. So every time we run a point estimate off of a sample, it's going to change. It's going to be sometimes very close to the population mean, sometimes not really that close at all. Over time, we will see that in general, the larger the sample size that we take from the 40, the closer our sample mean will be to the population mean. And that we will very, very rarely get a mean that's more than 2 standard deviations away from the population mean. So we have some confidence about our selection, but it's not perfect. So that's our sampling error. The sampling distribution is the distribution of all those point estimates from all possible samples from the population. So all that's saying is if we were to record, like they do in this thing, all the means, and then take a histogram, this is our sampling distribution. We can also calculate confidence intervals, which we're going to do next week. Those are the intervals around the point estimate that tell us how where the true value of the population parameter is likely to fall. So we, like, in terms of how would you hear that being articulated, someone might tell you the mean is 105 plus or minus 5. So they're saying the mean for that sample is 105 based on this estimate, but the true mean for the whole population is likely to be between 100 and 110. So it gives us an idea of how confident we can be in that estimate. A larger confidence interval means we're less confident. If we say that our estimate is unbiased, then that means that our sampling distribution matches the true value of the population parameter being estimated. So in other words, if our population is normally distributed, then our sampling distribution would be normal. And then the standard error of an estimate is the standard deviation of the sampling distribution of the estimate. So it's telling us how much our estimates vary from sample to sample. And we'll take a look at these in a little more detail. So they talk about the sampling distribution of the sample mean as X bar. And it's our unbiased estimate of the population mean. And so it's just represented by mu, which is our mathematical symbol for mean. The standard error of the sample mean is the standard deviation divided by the square root of the sample size. And we can calculate this pretty easily in Excel because we have the standard deviation function and we know our sample size. So it's just a matter of plugging things in. No crazy math required. That you might see with small s, which is fine. So that's just the sample standard deviation because we often don't know the population standard deviation. And then when I mentioned saying, for example, the population mean is 100 plus or minus 5. So to calculate the interval where we're going within 2 standard errors, we can estimate that. So we can get a 95% confidence interval with this equation right here. And we're just going to pull up what these calculations look like in Excel, because what's really important to me is that you just understand how to get there from Excel. So let me pull up that example. Okay. So we calculate the mean from this sample. We have a population of 1,000 and a sample size of 100. So this is big N, this is little n. Here's our 100 items. So to get our mean, we take the average of all of the items in the sample. And then for the sample standard deviation, we use this function that we're very familiar with now, standard deviation.s, because it's the sample and not the population. If we had all, 10,000 items in the population, we could use the standard deviation.p, but again, that's rarely ever the case. So now we've got our standard deviation and our mean. To calculate the standard error, we take the standard deviation, which we just calculated, and divide it by the square root of our sample size. So that's it. And then we get this, this amount right here. So we believe then that the sample mean is going to be anywhere from this amount, the mean we estimated, minus this amount to the mean plus the standard error. So we can say with 95% confidence that our actual population mean of all 10,000, if we had all 10,000 and we calculated it, would be between $237.21 and I just realized I selected the $237 and $320.84. This right here is a correction that they talk about in a little bit later. If you don't have if your sample size ends up being a pretty large proportion of the population, then this calculation is less accurate, but we're not going to get too spun up on that. This is what I want you guys to focus on. Calculating the average, the standard deviation, and then taking the standard deviation, dividing it by the square root of the sample size to get your standard error, and just understanding that that's what this means. That our population mean is 95% likely to be between these two values. How did we get to, where were we? Okay. So what we were just talking about with that correction, normally our sample size is very, very small relative to the whole population. If that's not true, if the sample size is greater than 5% of the population, then there's this correction factor, which isn't really anything crazy in terms of a formula. We already had n and big N and little n. In this case, it was 10,000 and 100. So the correction factor is just the square root of the 10,000. Am I even looking at? Yeah. Minus 100 divided by the population size minus 1. And then they multiply that by the standard error to give it a correction. So the actual correction is, let's see, I actually want this as a percentage. So it only was off by about 0.5%. So the correction factor just multiplied this amount by, now I changed that, by like 0.05 and so percent. So it ends up being very, very close and kind of nothing that we would stress out about. That correction grows, though, the larger your portion of the population the sample size is. So eventually your estimate may not be very accurate, and that's why you would want to add in the correction. We won't need to do that for our exercises. Okay, so I'm going to take a break here because when we come back, we're going to talk about the central limit theorem, and we're going to talk about what that means and apply it to the Wheel of Fortune example. So let's take a break and we'll come back at 2 and we'll go through that information. Okay. Jumping back in to the central limit theorem. I'm going to try and break this down a couple different ways to help explain it. But the premise is that whenever we have a population distribution that has a mean and a standard deviation, then the sampling distribution of the sample mean is approximately normal. And this approximation improves as n increases. So the key here is the term normality. When we sum or average n randomly selected values from a distribution, the distribution of the sum or average is approximately normal, provided that n is sufficiently large. So this is why we covered normal distribution so heavily last week. And what this looks like, so we're going to do the Wheel of Fortune example, but I'm going to kind of go through this conceptually first. So if we're spinning a wheel, what color do I feel like? And we only spin once. So let's say n, we're only spinning once. The probability, the uniform density function, so where our probability is from 0 to 1, that our spin is going to be between 0 and 1,000, the average. So whatever we spin, let's say we spin and we roll up 400, the average of that is 400 divided by 1 because we only spun once. So we have this rectangular uniform density function. It is guaranteed that the average spin of one spin is going to be between 0 and 1,000. Okay, so let's make this like slightly more interesting. Let's say that we spin twice. So the first time I spin twice, I might get 800 and 200, and so 500 is where my roll happens. And I could do this, you know, a bunch of times, and I'm going to get averages that are pretty uninteresting. Since we're only rolling twice, you know, there's times where I'm going to roll 2 really high numbers and get a pretty high average. And so my distribution might look something like this now, where I'm just taking the average of 2 rolls, and then I'm doing this over a bunch of trials and plotting the means that I get for all of those trials. So let's say now that we spin 10 times, and each time we get, and we average those 10. So if you think about this, if I spin twice, there's a pretty good chance that I might get too high spins. And so that's why my distribution looks pretty flat. Because I'm only rolling twice. And so the odds are kind of in my favor there. The more spins I have to take and then take the mean of, the less likely I'm going to get a bunch of spins that are high up in between 900 and 1,000, or that are really, really low. Because in order for if I say n equals 10, in order for me to get a sample mean of 150, somewhere in here, I would have to roll 10 times, or I would have to spin 10 times and get pretty low numbers all 10 times in order for the average to be that low. So as n increases, that the average is going to more and more fall toward somewhere around 500. So let's clear this. Okay. So let's say now I do a histogram of my winnings from my 10 rolls. So I don't get very much stuff down here. And remember, the sum of all of these probabilities will equal 1. And I'm sorry, I'm not a great artist, but I just want you to get the picture. So it might look kind of something like this, where if I spin 10 times and then I take the mean of that, I'm going to come out somewhere around 500, and these values become way less likely. So you can see this curve, this normal curve starting to form, and the more you increase n, the more you're going to approximate the normal distribution. So if we did like 100 spins, our histogram would look, it would have like a bunch of lines, and it would look really, really nice. And we could break up the intervals more and more, but we'd have a much nicer looking graph, and it would be nearly approximate to the normal. So that's the big takeaway from the example in the book that we're going to go through, which is the spinning in the Wheel of Fortune. So in Excel, we're going to illustrate the same thing I just showed you. So our population is the set of all outcomes you could obtain from one spin of the wheel. So 0 to 1,000. And each spin gives you a randomly sampled dollar value. And then we're going to replicate that with n spins and calculate the average winnings from n spins, and then plot them on a histogram. We're going to look at that histogram and how it takes on more of this bell shape. So if we do single spins, we get this kind of flat distribution. If we do 3, we start to actually pretty quickly see a bell curve forming. Okay, so they've taken our Wheel of Fortune scenario and created a simulation where the max number of winnings is 0, or the min number, and sorry, it's almost Friday, and the max number of winnings is 1,000. And so for now, we're just doing one spin. And they've done some fancy stuff in here, but they have this this formula that says if this spin right here is less than or equal to the number of spins, then we're going to populate something in this column. Actually, yeah, let's do it this way. We're gonna calculate something. If this number is greater than this number of spins, then this formula is saying just do nothing, like leave the cell blank. So if you have an if formula and you want to leave a cell blank, this is how you do it. 2 quotations. Okay, so now let's look at the actual how they're getting a random number here. Okay, so if the spin number is less than the number or equal to the number of spins, calculate. So take the minimum winnings and then add the maximum minus the min. So basically the range. In this case, because the minimum is 0, all we're saying is take the amount of money that you could win, so $1,000, and then multiply it by the random function. So the reason that this is more complicated than it needs to be, like for our example, we could have just said take cell B4 and then multiply it by the random function. But they set this up for you so that you could run the simulation and change the parameters and it would still work. So for example, if you said like you're going to win between $500 and $1,000 every time, it would still work. It would just say, okay, so you can win up to $500. So take $500, multiply it by the random function to get my random number. And then if that ends up being like $200, my winnings is the 200 plus the minimum winning of 500. So that's all that's doing. It's trying to be flexible for you. But in this case, we're getting a random number between 0 and 1,000. That's kind of the key point. And if we change the number of spins, now we'll get 2 columns of data. So that's why they set that if formula up that way. I would encourage you to look at this. It's very clever, and it's something that you might actually end up doing. And this is something I do all the time. There's another function called if error. So sometimes I'm doing a model and I'm calculating like row percentages, and occasionally I have a value where, oh, it's going to recalculate every time because of that random function. Ignore that. But if I like have some values, if I'm just going through a generic formula and I end up dividing by 0, for example, what am I doing? So like, let's say it does this, it's going to give me an error, and because I can't divide by 0. So if I'm working on something and I'm okay with that error existing and I just want that cell to return nothing, if there is an error, I can use this if error function, and then I have my value I want it to calculate, and if it returns an error, it just leaves the cell blank. So you can see, like, because what happens is, like, if I have a sum and one of the cells has an error, it won't sum. So I want to make that go away. So I use that that blank cell option with if formulas and if error formulas all the time. So it's definitely worth kind of noting. Okay, so the point here, so every time we increase the spin, we're going to get more and more bell-shaped looking, a normal looking curve. You can see, like, it approaches pretty quickly, which is pretty cool. And you can see every time I increase this formula is saying if 6 is less than or equal to 6, which it is, then calculate it, otherwise leave it blank. So that's why 7 is empty. So we can just keep going, changing our simulation. Whoop, no spins, all the way to 10 spins. And you can see, like, the more spins you do, the less likely you are to get these extreme values because of the averaging that we're doing. So I think this is a pretty cool way of looking at this and seeing how things change. You can also see the standard deviation changing. So look at when we do one spin, the mean is still around 500, but look at the standard deviation. It's like huge. Let's see what like 3 spins does to our standard deviation. So our mean fell right in line with 500, but our standard deviation is smaller. If we go to 5, our standard deviation is even smaller, down to 107. And then by the time we get to 10 spins, the standard deviation is, in this simulation, was 88. So you can see the larger that n is, the more accurate or the better approximation our sample parameters are to the population, the less sampling error. Okay, so again, we have this problem where we want to select the appropriate sample size. The more complex our issue is, what we're surveying, what we're doing, the harder that it's going to be to get a decent error. So increasing our sample size helps kind of fix that, minimizes the sample error. But, you know, then we got to balance that with cost, collecting data in a timely manner. If we're surveying 100 people versus like 1,000 people, that's a significant increase in the time it would take to collect that data. And then the more surveying you do, you actually increase the chance that you're going to have some kind of non-sampling error. So if you send out a survey to a really large number of people, it just increases the likelihood that a really large number of people aren't going to respond. Okay, so to recap, when we estimate a population mean with a simple random sample, then our sample mean is a point estimate. It's close, it's a best guess. The accuracy of that point estimate or that best guess is measured by standard error, and that is the standard deviation of the sampling distribution of that point estimate. We can calculate a confidence interval for the population mean. It's about 2 standard errors on either side of the sample mean. From the central limit theorem, our sampling distribution of the sample mean is approximately normal when n is reasonably large. There's about a 95% chance that any particular sample mean will be within 2 standard errors of the population mean. And we can reduce sampling error by increasing sample size. Okay, so before we move on to discussion, which we have a lot of time for, are there any questions about this material? And I'm actually thinking we'll kind of touch on the homework first and then do our discussion at the end, if that's okay with everybody.
I think that's a great idea.
Okay, so let's look at our assignment. The first couple of questions are conceptual, so those will come from your reading and what we talked about in class. But what I want to review with you is what's expected of you from the Excel calculations for this week. So let me pull up my information. Okay, so they're going to give you a file which has, let's just open it, a bunch of service times. I'm waiting for it to open, sorry. Okay, so I have all these customers, and I have their corresponding service times. Wow, look at all this. There we go. Okay, so you're going to take this information and we're going to figure out how to take a random sample size of 30 from the data. We're going to calculate the sample mean and the sampling error. And then we're going to calculate a good approximation for the standard error of the mean. And then finally, this last question is directly from the book. So there's a little tidbit in there about how the standard error and sample size are related. There's a ratio between the two. I love how they tell us this is fictitious data, like it matters. Okay, so let's just kind of walk through this. So first we want to create a random sample of 30. So we're going to use the method that we used for the simplified sampling in example 1. And I'm going to collect, okay, so see what this is a very ineffective way of highlighting data. A better way to do this is to click at the top, hit Control Shift and the down key, and then hold Shift and click over, much faster. So I'm going to copy this. I'm going to paste it over here. And then I'm going to generate. So I'm going to actually, well, it won't. Yeah, I'm going to have to drag it. I'm going to drag the formula down. And then I'm going to select and sort now. So Control Shift down, over. And I'm going to come up here. I lost some of my, to expand this, sorry. Okay, filter. You can do this multiple ways. You could do like the highest 30 or the, I just realized I have to do a custom, sorry. So I'm sorting on my random numbers, smallest to largest. And why didn't it? I think I might need to turn off. It recalculated when it did that. Yeah, okay. It's 1 second. So if it's doing this to you, like it's sorting and then recalculating, and so it's messing up my, oh, I know why. Does anyone remember what I forgot to do? It won't work unless you take your random. So remember I was telling you that random function recalculates every time you change a cell. We have to paste these as values. And now we can sort. Okay, so I'm sorting smallest to largest. You could do it largest to smallest if you wanted, doesn't really matter. And then I'm going to take the top 30, and there's my sample.
How did you paste them as values?
So to paste them, you go highlight them, copy them, and then right click, and then click this paste options as values.
Got
It's
it.
got
Thank
the
you.
little clipboard with the 1, 2, 3.
Yep, I got it. Thank you.
Yep.
I just missed that last part.
No problem. Okay, so now we have one random sample. Interestingly, pull this back up. Okay, so then from there, we would create our sample mean. Oop. Type. And we can actually also calculate, because we're going to need to know it, the population mean. And then what else do we need to know? Point estimate. Okay, so how do we calculate then the sample mean? Anyone?
So it says use the average, median, and standard deviation functions. Trying to find.
Yep. So sample mean is going to be the average of our 30 samples.
Hmm.
So then the population mean will be what?
That'd be the median?
Nope, just the average of
Oh, just the population. I'm sorry.
population. Okay. So our sampling error is just going to be the difference between the two. And then I will leave the standard error up to you guys. It's in the book and in the examples. It's just going to be you'll need to calculate the standard deviation of the sample. So if you need to remember that function, that's the right there. And you're going to want to also record probably your sample size. And then you're going to take the standard deviation divided by the square root of the sample size. So I'll let you guys calculate that one on your own. And then this last question, we can talk about, there's a little tidbit in the book that talks about like how these things are proportionate. And so if you want to, because the standard error is inversely proportional to the square root of the sample size, that's based on that formulation, that calculation, then that means if you want to decrease standard error by some factor, you would have to increase the sample size by a much bigger factor. So if you want to decrease standard error by a factor of 2, you have to increase the sample size by a factor of 4. So that is a hint to that question. And that's also why accurate sampling is so expensive, because that means if you have a sample size of 100 and you want to reduce your standard error by a factor, like if you want to reduce it by a factor of 2, you would have to then increase your sample size to 400. So with bigger sample sizes, you can see how quickly that would escalate and become kind of infeasible. So for your homework, pretty straightforward. Hopefully that helps you guys get started and kind of get your spreadsheet set up. Make sure to use good spreadsheet modeling. I didn't really think that wasn't the most attractive spreadsheet that I could have done, but there you have it. So, all right, let's spend the rest of our afternoon having our discussion on prescriptive analytics, and then I'm going to let you guys go a little bit early since we have gone over the past few weeks in the past, and just kind of even things out a little bit in terms of class time. So let me just cover a few things really quickly. Okay. So prescriptive analytics is, let me share my screen. That would probably be helpful, right? Okay. So prescriptive analytics has evolved so much in the last couple of years, and there's a couple of reasons for that. One is just the availability of data. We are able to capture so much data now and store it. If you think about like just like SD cards and how expensive like a 1 gig SD card used to be, and now you can easily, very cheaply buy like a 500 gig or even terabyte card, and they're just, yeah, it's just storage of data is so much cheaper and easier to do. And we have the cloud now, so you don't even necessarily have to get large servers involved. You can do infrastructure as a service and use somebody else's servers. So lots of things have changed in the last couple of years that have really made it possible for businesses to capture just enormous quantities of data pretty cheaply. The tools available for prescriptive analytics are getting easier to use. Less coding, kind of more off the shelf, out of the box solutions, friendlier user interfaces. They often have like reporting functions now that help higher level managers kind of understand what the software is doing and what the results of the software are. So the whys and hows. If it's easier for stakeholders to understand, then they're more likely to get on board, which makes it more likely that people will use these methodologies. The tools are also more sophisticated, so we can run optimizations with like it's just an absolutely insane amount of variables and put in so many constraints. And there, toward the end of this course, we talk about optimization, and we look at some really simple optimization models with just a few constraints and a few variables, and you can see you'll get an idea of how quickly how complex these problems get very quickly when you're trying to calculate things out by hand, or even calculate them in like with spreadsheet software. But with computer programming now, these tools can run them no problem, and they're quick. We can do all kinds of what if and scenario analysis with just massive amounts of data. And then finally, businesses are just using these things more. They're kind of seeing the trade-off. So like optimization was very common in original equipment manufacturing. So like a Boeing plant wants to make sure that its production schedules and its manufacturing is using as little waste as possible and using all their resources in the smartest way possible. And so that was very common, but they weren't using these optimization type modeling for things like their finance issues or other aspects of their organization, like their portfolio analysis. So how are they investing in projects, stuff like that. So they've just been a bigger part of the business, and also playing a bigger role in how managers and leaders make decisions within their business. It's also, prescriptive analytics is one of the harder analytics for people to kind of wrap their minds around. We talk about the difference between predictive and prescriptive. Predictive is kind of saying like what might happen or what will happen, and prescriptive is saying like what should happen. So like what should you do in order to get the best results? So it's prescribing a solution as part of the problem. And so some of these things might look like these types of models. So long-term planning, so that would be like all your capital expenditures, all your projects. How should you invest in them to maximize your return on investment and capital? If you had a factory and you were trying to figure out like inventory strategies or how to produce certain products, manufacturing, there you could use a prescriptive model for that. So in terms of like inventory strategy, you could think about like Amazon and how they map out their inventory and decide how many of any particular item to keep in a warehouse in any geographical region based on what the people nearby are ordering. And they will actually even, if they have like limited stock of an item in one warehouse, but they know based on their consumer behavior that they're likely gonna need some more in the next week, they'll like preemptively ship more over. And they, before, you wouldn't have been able to like optimize that way. You wouldn't have been able to predict behavior at that kind of level. Like Amazon basically knows what you're gonna buy before you know you're gonna buy it. Like they're this close to being accurate like that. And so they plan around that. Operational planning models, so production sequences, shifts. So like in healthcare, how should I do my nurses' shifts based on caseload and what's going on in the world, things like that. Distributing goods, freight, and logistics. So this is kind of where prescriptive really started. Truck loading, order handling. How do you optimize the routes that a truck would take to ship goods throughout the country? All of those things can be modeled, and all of these constraints could be added on, and all these variables like weather and predicted weather forecasts and like your fleet and drivers, and you could throw in variables like how, if you have data on how